Hi, this is Dr. Michael Wenzel, and I'm going to introduce to you today about this lab you're doing on self-healing hydrogels, which we call smart materials in the classroom. The fun example analogy we have is a magician's assistant being put into a box, and then the material being sawed in half as in the box, and then magically it gets self-healed, and then it recovers completely. So we're actually going to use this in chemistry terms, where we're actually going to use a material, a self-healing hydrogel, that is able to recover completely. This work is a collaboration between Augsburg University and actually Ripon College. It involved my good friend, Professor Patrick Willoughby at Ripon College, and two of his students, Riley Morris, Albie Hilker, and an Augsburg student, Taylor Mattice, who recently graduated and is now at medical school. And they combined to help to create this lab. As the name says, Hydrogels is a water gel. Hydro as in water, hydrogel. There's many examples actually found in modern medicine. These hydrogels are often very biocompatible, very, very biocompatible. One example is transdermal drug delivery. So literally on the skin, a patch. A hydrogel could be part of a patch that could help deliver drugs. It's useful in wound dressing, right? These are all very biocompatible. Again, water is a major part creating this gel. Contact lenses are actually made of hydrogels. So right, again, most of context is actually water is in there. It's a gel, it's a hydrogels. Drug delivery system is actually in the body. So as a pill you'd swallow, that could be part of that pill could be a hydrogel that could help encapsulate or hold in a drug that you want to be delivered. And also tissue engineering, where actually artificial skins can be started to think about. That's kind of the next level of what hydrogels could be. Again, hydrogels are very biocompatible, and they consist mostly of water, right, gels. But you can see how they can be very, very biocompatible in lots of different examples and how they can be really important materials. The hydrogel we're going to work with is self-healable PVA. PVA just stands for polyvinyl alcohol. So just for poly, meaning many, vinyl, alcohol. So hydrogels are polymers. Right? So what does a polymer look like? A polymer consists of monomers, and then these monomers are repeated over and over, and they create polymers. So monomers are what create polymers. This is an example of a polymer. And they draw in these special ways to show how that's a repeating unit. But if you were to look, if I were to circle, here you can see there's the piece, there's one monomer, there's another monomer, and there's another, and there's another, and it keeps on going. You can see what part is missing is this alkene double bond, because that's the part that reacts in actually creating the polymer. And the interesting part of these, we're going to make these self-healable. So polyvinyl alcohol, which is this right here, polyvinyl alcohol, is actually what we're going to use to make a self-healable hydrogel. So here we're just going to give you a quick picture of what we're going to start with and what we're going to end up with. So again, just to emphasize, polyvinyl alcohol, that's a repeat unit. This is the abbreviated structure. Just at the N would indicate the number of monomers incorporated in this polymer. So it's going to be a long chain molecule. It starts out as crystals, and then it actually becomes this gel, right? So the crystals, we're going to stir this and absorb water, and then we actually get a gel. And the reason we get a gel is the interesting next part. So hydrogels are cross-linked. So imagine all the hydrogels, those polymers, are these long chains, all these long chains. And these portions right here, we call those crosslinks. So they're combined, they're basically connecting all these long chains. Right? And what that does is when you connect those long chains, you get much more of a solid structure. Right? You can think of the noodles by themselves, the long chains by themselves, have much more flexibility, but once you start making these crosslinks, all these circle crosslinks, it becomes much more of a rigid structure, right? So it creates that gel-like nature. So it's no longer going to be dissolved, it's going to be it's actually going to be a gel-like nature. Now there's lots of different ways we can do this. One of the most common ways you probably have heard of is actually using an external chemical and actually using polyvinyl alcohol and maybe borax. This is that classic slime experiment. So So many of you have done this. So it actually is taking the same material we use today, polyvinyl alcohol, but to create those crosslinks, right, they actually add an external chemical agent, borax. So the borax, as is shown here, creates these crosslinks. So it takes an external chemical to create those crosslinks. That's how you create that slime. But we're not going to need an external chemical. In our case, we're just going to freeze it. And what happens when you freeze this, essentially the water gets trapped and forms like these little crystal structures, right, where this hydrogen bonding that's going on creates the crosslinks. So the hydrogen bonding creates the crosslinks. So instead of using borax, so no borax this time, we can get away with just freezing it at -20. We actually create this order, and we get this hydrogel by doing that. And we get that order just by doing that. So no external chemical reagent, which is very important as we go forward. All right, so here's just a picture of what it looks like. So this hydrogel has been cut, and it's starting to self-heal. So what happens, how does it actually self-heal? That's an interesting question. Let's look at this so you can actually see a picture. Let's look at another picture. You can see it essentially stretching out. There's the fracture area, so you can really see you can pull on this and it re-heals. But how does it actually re-heal? It's another picture to see that. So this is a hydrogel that's been cut, and one of the pieces was actually dyed with a blue dye. And you can see here, all of a sudden some of that blue color has come over. And what happened is this. You can think of both sides of fractured material. One was completely blue, one was colorless. What happens is on the surface, you can't see this, but imagine there's little bits of polymer there, right, on both sides. And you can't see this. This is on the microscopic level. And once you bring these two things back together, what happens is those chains on the surface, all right, on those chains on the surface, once they're in contact with each other, they kind of flow across, and they can recreate that H bonding, that hydrogen bonding. All right, they recreate that H bonding. That's the most important thing. These long polymer chains are kind of finding each other again and can redo that H bonding. And what you see here, the reason why you see color is because when these polymer chains were moving back across, they brought some of the blue dye with them. Right, so that's why you're seeing this blue color here, is because the dye molecules were kind of mixed up, right? Kind of mixed up with all the surface here, and that came across. So you actually can see a color of that happening. So the blue dye has nothing to do with the healing. It's just being drug across, stuck within the polymer, the long chains, as they start to redo that H bonding. So that's the key here, is it heals because of hydrogen bonding. So let's bring this home to talk about green chemistry a little bit. How is this a sustainable method? And we obviously talk about this being very biocompatible. I would say it reduces a lot of waste. Right? We're not using a lot of waste here. We're using water. It's atom economical because we don't need an external agent. Is less hazardous. Again, we're using water, a hydrogel, but no, we don't need borax or anything like that. It's not actually designing anything. We're not really designing any chemicals. Safer solvents? Heck yeah, water again. Water is a great solvent to use. It could be more energy efficient, right? If we don't have to use chemicals that need a lot of energy to be made, and we didn't heat this up a lot, so they can be maybe energy efficient. Unfortunately, well, it's not made from this material is not made from renewable feedstocks, but you could think of hydrogels that could be made from renewable feedstocks. We didn't use derivatives. Again, no external agents, no catalysts. This is not designed for degradation, but if something's self-healing, it can be reused maybe more than once. So it doesn't necessarily degrade, but it can be reused multiple times. I would again argue it's also maybe real-time pollution prevention, because again, these type of materials, if they're self-healable, they can be used multiple times. So you're not cycling anything or burning anything. You actually can reuse this material over and over. And then maybe you could even say it's safer chemistry for accident prevention if all these hydrogels are being used for biocompatible uses, such as drug delivery, or cell or tissue engineering, all those kind of things can also be maybe ways to prevent accidents as well. So finally, we're going to get to what you actually need to do today. So what you guys are going to do first is you're going to take the hydrogels that we have already made for you, and you're actually going to take scissors and cut them. You're going to let them push them together for 30 seconds, and then put them back into the mold and allow them to heal for 1 hour. After an hour, you're going to actually measure the tensile strength, which is something similar to what you've done before, and see how many newtons it takes to force them apart. During this inactive hour, what you'll actually be doing is part 1 of the experiment, and that will be preparing hydrogels for a lab on Thursday. So again, all you're going to do is create an aqueous solution. So we want to take polyvinyl alcohol, and we're going to add water to it, make the hydrogel. At that point, we're going to freeze it. This will be the lab instructor will freeze it for you, and then before Thursday's lab, we'll thaw these, and then they will go to the self-healing studies. Really hope you enjoy this lab, and we'd love to hear your feedback on all of it as well.